This example gives you the basic framework for adding vectors analytically. This is important because it allows us to get actual numbers for the addition and subtraction of vectors. In the first part of this example, we're going to add two vectors. Vector A has a magnitude of 34.0 meters per second, so it's some sort of velocity vector, and it's directed at an angle of 45 degrees. Vector B has a magnitude of 20.0 meters per second, and it is directed at an angle of 123 degrees. And the question is, what is the sum of vector A plus vector B? Now in the text, I actually add these vectors graphically to begin with in order to give you an idea of what the final result will look like. I'm not going to do that here because I really want to concentrate on how to add analytically. So let's just try and figure out what the magnitude and direction of A plus B is. Now the way that I add vectors analytically is I break them down into their x components and y components. I do this because their x components can add directly, and their y components can add directly. So if I break these vectors down into their components, I can add each of the components, and that will give me the final vector. So let's break these vectors down into their components. We'll start with vector A. The x component of vector A is calculated by taking the magnitude, 34.0 meters per second, and multiplying by the cosine of the angle, 45 degrees. When I do that, I get 24 meters per second. I'm limited to two significant figures because 45 has only two significant figures. The y component of vector A is calculated by taking the magnitude once again, 34.0 meters per second, and multiplying by the sine of the angle, 45 degrees. When I do that, I once again get 24 meters per second. All right, we're only halfway done. We also have to break vector B into its components. The x component of vector B is calculated by taking the magnitude, 20.0 meters per second, and multiplying by the cosine of the angle, 123 degrees. When I do that, I get negative 10.9 meters per second. The y component of vector B is calculated by once again taking the magnitude, 20.0 meters per second, and multiplying by the sine of the angle, 123 degrees. When I do that, I get 16.8 meters per second. In each case, I can keep three significant figures because both the magnitude and the direction have three significant figures. Okay, so now that we have these vectors broken down into their components, all we have to do is add the components. For example, let's call the sum vector C. If the sum is vector C, then the x component of vector C is simply the x component of A plus the x component of B. Well, the x component of A is 24 meters per second. The x component of B is negative 10.9 meters per second. When I add those, I get 13 meters per second. Now before we move on, I want you to look at significant figures here. At this point, we're adding. When we add, we have to look at decimal place. We don't count significant figures. We're adding 24 to negative 10.9. 24 goes out to the ones place. 10.9 goes out to the tenths place. So my answer can only be reported to the ones place, and that's why the answer is 13 meters per second. Now let's go on to the y component of the sum. If we're calling the sum vector C, then the y component of vector C is simply the y component of A plus the y component of B. The y component of A is 24 meters per second. The y component of B is 16.8 meters per second. So the sum is 41 meters per second. Once again, we're limited to the ones place because of 24. Okay, well now we have the components of the vector sum. The sum of A plus B has an x component of 13 meters per second and a y component of 41 meters per second. In principle, that answer is good enough. However, physicists typically talk about vectors in terms of magnitude and direction. So now that we have the two components, let's go ahead and convert them into magnitude and direction. Well, to get the magnitude, we take the square root of the x component squared plus the y component squared. That's the square root of 13 meters per second squared plus 41 meters per second squared. That turns out to be 43 meters per second. The direction is calculated from the equation theta equals the inverse tangent of the y component over the x component. The y component's 41 meters per second, the x component's 13 meters per second. The unit cancels, which is important. There should be no unit inside an inverse tangent. And when I take the inverse tangent of 41 over 13, I get 72 degrees. Now we're not quite finished because we have to make sure that angle is properly defined. The only way to do that is figure out where this vector is on the Cartesian coordinate plane. The x component is positive, which means it's to the right of the origin, and the y component is also positive, meaning it's above the origin. So this vector is to the right and above the origin, which is quadrant 1. In quadrant 1, we do nothing to the answer that comes out of the calculator, so 72 degrees is the properly defined answer. So the final result is that A plus B has a magnitude of 43 meters per second and an angle of 72 degrees. Now the second part of this example is very similar to the first part of this example, so I'm not going to go over it. I will make one point, however. When you get to the place where you're adding the x components of vector A and B, remember that you're adding, so you have to follow the rules of addition when you're dealing with significant figures. Thus, you report your answer to the same decimal place as the least precise number in the problem. Remember that.